The passage is explaining what deadlocks are in operating systems and why they happen when multiple processes compete for exclusive resources. A resource is anything a process must request, use, and later release. Some resources are hardware devices like printers, scanners, Blu-ray writers, or tape drives. Others are software resources like database records, files, or internal OS table entries. The key point is that many of these resources can be used by only one process at a time, because simultaneous use would corrupt output or data. A deadlock occurs when processes need more than one resource and acquire them in a conflicting pattern. The example is, process A grabs the scanner first, process B grabs the Blu-ray recorder first, then A asks for the Blu-ray recorder and waits, while B asks for the scanner and waits. Each is waiting for the other to release something, so neither can ever proceed. The same kind of deadlock can happen over a network when devices are shared remotely, or in databases when transactions lock records in different orders. The text then distinguishes two kinds of resources, preemptible and non-preemptible. A preemptible resource can be taken away safely by the operating system and given to another process, like memory on a system that supports swapping or paging. A non-preemptible resource cannot be taken away without risking failure or corrupted results, like a Blu-ray writer in the middle of burning a disk. Most serious deadlocks involve non-preemptible resources because you cannot simply steal the resource to resolve the wait. Next, it describes the typical life cycle of resource use. Request, use, release. If a resource is unavailable, the requesting process either blocks automatically or loops and retries. For discussion, the chapter assumes the process is put to sleep when denied, meaning it cannot do useful work until the resource becomes available. The chapter shows how programs often manage resource acquisition using semaphores or mutexes. Each resource has a lock initialized to 1. To acquire the resource, a process does a down operation lock, then uses it, then does an up operation unlock to release it. The problem appears when a process needs multiple resources, it locks them sequentially. If different processes lock the same set of resources in different orders, a deadlock can occur. That's the big coding lesson in the figures. If process A locks resource 1, then resource 2, and process B also locks resource 1, then resource 2, the system is deadlock-free. One process may wait, but eventually it proceeds. But if process B locks resource 2, then resource 1, while A locks resource 1, then resource 2, you can get the classic cycle. A holds 1 waiting for 2, B holds 2 waiting for 1, and both wait forever. A tiny change in lock ordering can be the difference between correct code and a rare, hard-to-reproduce failure. Then the text gives a formal definition. A set of processes is deadlocked if each process is waiting for an event that only another process in the same set can cause. Usually that event is release a resource I need. Since none of the deadlocked processes can run, none can release anything, so the system stays stuck indefinitely. This is called a resource deadlock, and it is the most common type discussed. Kaufman's 4 necessary conditions for resource deadlock are the core theory here. 1. Mutual exclusion, meaning a resource is held by at most one process at a time. 2. Hold and wait, meaning a process can hold one resource while requesting another. 3. No preemption, meaning the OS cannot forcibly take the resource away. It must be released voluntarily. 4. Circular wait, meaning there is a cycle of processes where each waits for a resource held by the next. All 4 must be true simultaneously for deadlock to be possible. If you prevent even one condition, deadlock cannot occur. To reason about deadlocks, the chapter introduces resource allocation graphs. Processes are circles. Resources are squares. An arrow from a resource to a process means the process currently holds that resource. An arrow from a process to a resource means it is blocked waiting for it. When there is only one instance of each resource type, a cycle in this directed graph implies a deadlock. The cycle literally represents A waits for something held by B, B waits for something held by C, and so on until someone waits for A. The longer example shows how scheduling choices affect whether deadlock happens. The OS can interleave processes in many ways. One interleaving of requests creates a cycle in deadlock, but a different interleaving avoids it. This sets up the later idea of deadlock avoidance. An OS can sometimes refuse to grant a request immediately, or delay scheduling a process to prevent the system from entering a state where a future deadlock becomes inevitable. Finally, it lists 4 broad strategies for dealing with deadlocks. 1 is to ignore them entirely, the ostrich algorithm, which is common when deadlocks are extremely rare and prevention would cost too much performance or complexity. 2 is detection and recovery. Let deadlocks happen. Detect cycles, then recover by killing or rolling back processes or freeing resources. 3 is dynamic avoidance. Carefully decide whether granting a resource request keeps the system in a safe state. 4 is prevention. Design the system to structurally break one of Kaufman's conditions, like enforcing a global lock ordering to eliminate circular wait.